So over the next couple sessions, we're going to be talking about these different stages of stellar evolution, going through the life cycles of low mass stars and high mass stars. But for this session, we're going to start by looking at how stars originally form. How do we go from one of these giant molecular clouds, which are these regions in space where there's cold, slightly denser gases, and how do we actually form main sequence stars? Just remember our definitions of main sequence stars. The two requirements for a main sequence star is it's in gravitational equilibrium and it's fusing hydrogen into helium inside of its core. So how do we go from one of these giant molecular clouds to one of these main sequence clouds? That's what we're going to focus on for this session, and then later talk about evolution of low mass stars, high mass stars, and the different types of dead stars. So here's the very, very quick overview. We start with these giant molecular clouds, these clouds of dust and gas in space, and something disturbs those clouds. There's a shock wave from a supernova passing by, or some of these clouds run into each other, and something starts this thing collapsing. Gravity takes over and starts collapsing it even more, and we actually get multiple stars being formed out of each of these collapsing giant molecular clouds. And these collapsing stars, these collapsing clouds of gas, they do have some rotation. So as they're rotating and collapsing, there's going to be that conservation of angular momentum idea where that thing's going to start spinning a little bit more. Most of that material falls to the middle in what's going to be our protostar, and the rest of that spinning material is going to end up forming a disk. That disk rotates faster and faster, and that's going to be the material that is eventually going to form planets in this star system. And in the middle, most of that material is still collapsing inwards, creating higher densities, higher temperatures, higher pressures, and eventually that's where our star is going to form. So we're going to be spending some time going to more of the details of this. And let's start by talking about these giant molecular clouds. So we start with a giant molecular cloud. Now, when we say giant molecular cloud, we really mean this. The typical clouds are around 50 to maybe a couple hundred light years in diameter. So this is literally millions of times larger than our own solar system. And these cloud masses can be around 1,000 times the mass of the sun. Remember that these clouds aren't going to form single stars. We're going to see that this forms an entire cluster of stars. So they're very large. So around 1,000 times the mass of the sun. And 50 to hundreds of light years across. And they're cold. So these clouds of dust and gas, by cold, I mean around 10 to 30 Kelvin, which is around negative 260 degrees Celsius. So these are 10 to 30 degrees above absolute zero. So 10 to 30 Kelvin, where at these very low temperatures, this hydrogen is going to be in molecular form. So we get this molecular hydrogen gas, H2. So throughout this whole description of how stars work and how stars form, there's going to be two forces that are always either working against each other to some level. The inward force of gravity trying to take this mass, that gravitational force is always attractive, trying to compress that mass downwards. Fighting against that is going to be the effect of thermal pressure. If I have a higher temperature gas, higher temperature gases are going to tend to expand. So these two effects are always kind of battling each other. So let me write that one down. So inward gravitational force versus outwards thermal pressure. And as we talk about all the properties of stars and their different stages of evolution, it's going to be these two forces that are always battling against each other. And depending on which one may temporarily be winning out, well, that's going to determine how that star evolves. So if this is a giant molecular cloud that's primed and almost ready to form stars, it's going to have a very low temperature, so it will more easily collapse under gravity. So these giant molecular clouds, again, still by any definition on Earth, this would still be at a vacuum. But the little bit of dust and gas that's out there, the thin gases that are out there, the denser those gases are, the more likely gravity is going to win. And the lower the temperature, the more likely gravity is going to win because of that less thermal pressure. Composition, this is still going to be 3/4 hydrogen, 1/4 helium, and 2% other stuff. So 3/4 hydrogen, 1/4 helium, 2% other stuff. And that 2% heavier is from earlier generations of stars. Now, some of these elements, some of these heavier elements are bound up in molecules like ammonia, water, carbon compounds, but it's still mostly molecular hydrogen gas, so H2, and helium. Even though we call these giant molecular clouds, I'm not saying that they're primarily made of these complex molecules. It's still mostly hydrogen and helium. So here are some images. Let me actually zoom in on this so you can see this a little bit better. These dark regions that we're seeing, they're not just the absence of stars. What we have here is one of these clouds of dust and gas in space. And even though, as I've said multiple times, this would still be a vacuum by any definition on Earth, by any kind of comparison with things on Earth, these slightly overdense regions of gas block some of that background light. Again, these can be tens to a couple hundreds of light years across. So even though the gases are very thin, there's still a lot of that gas there because it covers such a large area. Same thing over here. We can see these giant molecular clouds blocking some of this glowing background light, either background light from stars or background light from some glowing gases, which we'll talk about later. Here are more structures of some of these globular structures in the Carina Nebula. So again, these are very, very thin gases, but looking on these scales, you can still see how they block some of the background light. And they have very, very complicated structures. We're still trying to understand how these structures work, what effects they have on star formation, what properties they have, how they get these particular structures. So these are Hubble images, specifically looking at ionized hydrogen, and some of the other colors in here are representing different kinds of molecules that show up in these kinds of nebulas. So the constellation Orion, if you're looking at the constellation Orion in the visible part of the spectrum, you'll see, okay, there are some bright stars making this shape that you may or may not recognize. If we want to find these star-forming regions that are at lower temperatures, what part of the spectrum might you want to look at? Again, these stars give off lots of visible light, but if I have lower temperature gases, what kind of light might they be giving off more of? Well, that's going to be the infrared light. If we look at the exact same region of the sky in infrared light, those lower temperature gases, again, they're at a low temperature, but they still give off a little bit of infrared light. You can also look at these gases in the radio part of the spectrum. Some of them have radio emissions. And we see these clouds of dust and gas show up much more brightly in these parts of the spectrum. In fact, the James Webb Space Telescope is specifically designed to look at its range of wavelengths that can detect are a little bit of red light but mostly into the near and mid-infrared part of the spectrum, specifically to be able to identify things like this. The James Webb Space Telescope is specifically designed to look at planets and forming star systems in other parts of our galaxy, and also look at very, very distant galaxies whose light has been redshifted. We'll talk about those sources later on in the course, but the James Webb Space Telescope is designed to look at these sorts of infrared sources. So we have this giant molecular cloud, this large cloud of cold, dense gas in space, and we want to know, how is this actually going to start forming stars? Well, again, it's going to be all about this battle between the inward gravitational force of all that gas gravitationally attracting each other and that outward push of thermal pressure. Initially, even though the temperature is very, very low, only like 10 to 30 Kelvin, these giant molecular clouds, they have enough thermal pressure to support themselves against collapse. But let's say there's some kind of disturbance. There's some kind of disturbance like a shock wave from a supernova, or two of these clouds colliding with each other. We're going to talk about how when galaxies collide with each other, that triggers a lot of star formation for exactly that reason. But in terms of this process, let's say there's some disturbance to the cloud that starts collapse. So some disturbance starts collapse. So the shock wave comes by, and that giant molecular cloud just gets pushed enough to start it getting smaller. Well, if I have this cloud of gas, and there's little bits of mass everywhere in there that are trying to pull inwards, if I take those masses and move them closer together, think about what happens to the strength of the gravitational forces between all those little pieces of mass. If I take those little pieces of mass and put them closer together, what happens to the strength of those gravitational forces? Well, if I take two masses and put them closer together, the force of gravity gets stronger. So once this cloud starts to collapse, those gravitational forces are actually going to get stronger and continue that collapse of this cloud. So we get that little bit of a disturbance, and then gravitational strength increases. So gravity increase and drives further collapse. And this collapse, at least initially, this thin gas that's pretty close to being transparent, it's very good at radiating away thermal energy. So at least at the beginning, this thing is going to start to collapse, but not heat up too much yet. So these are some images of examples of some of these shock waves. So these are some, I believe these are Hubble images, where there was I think this is just some very bright stars that have very strong solar winds, in the same way that our sun is giving off some particles in that solar wind. There are some very high temperature stars that are giving off a lot of solar winds, and we can actually see that shock wave moving through this cloud of gas. That shock wave, under the right conditions, these expanding shock waves, when they hit one of these giant molecular clouds, you can get those shock waves starting that initial compression of this gas, and then again, gravity will take over and continue that collapse and be ready to form some stars. So again, this is another one. Massive young stars have strong stellar winds, and that also can trigger some star formation to happen. So again, if we look at this same object in the visible spectrum and in the infrared, if I have one of these collapsing clouds of dust and gas, and maybe it's starting to heat up, well, if it's starting to heat up, some of the first wavelengths of light that it's going to be giving off are in the infrared part of the spectrum. So in the visible light, we don't get a super great view of what's happening inside of these clouds, but the infrared shows us a lot more detail about the stars that are just beginning to form inside of these giant molecular clouds. So how do we go from one of these dense cores to a protostar? So initially, the thermal energy, again, is easily radiated away because the gases are fairly transparent. Not perfectly transparent, but it's pretty good at radiating away that energy. So the temperature, at least initially, doesn't increase very quickly to balance gravity. And if I have one of these giant clouds, let's say I have one of these giant clouds out in space, would we imagine that one of these giant molecular clouds would have the same density everywhere throughout the cloud? Well, probably not, just because of random motions. There are probably going to be some areas that are a little bit more dense and some areas that are a little bit less dense. So we're going to get these slightly overdense regions showing up in this cloud. So these overdense regions, they will actually collapse more rapidly than the cloud as a whole. So when that original disturbance goes through, those regions that are already a little bit more dense than their surrounding neighbors, those regions are going to collapse first. So these collapse faster. And we get this effect called fracturing. Instead of just one giant star forming, remember, these original giant molecular clouds can be over 1,000 times the mass of our sun. Instead of making one giant star, these giant molecular clouds generate many smaller stars. So we produces many smaller stars of varying mass. We'll talk about the demographics of how many of each kind of star forms, but you're generally going to get more of the low mass stars, fewer of the high mass stars. These original clouds, at this point, were starting to crawl up on what might be considered a protostar. So these are originally spinning very, very slowly, very diffuse and rotating slowly. But as that material comes in, well, let me try to simulate this one more time. If that mass is starting really far out, and we have a slow rotation, well, if this starts really far out and there's a slow rotation, as gravity pulls that material inwards, that material is going to be spinning faster and faster and faster through that effect of conservation of angular momentum. So as this cloud collapses, the cloud is going to spin faster and faster. So let me change color. As these regions collapse, they start spinning faster. Due to conservation of angular momentum. That spinning material, if I have different clouds spinning in different ways, let me draw another diagram for this one. Let's say I have this cloud, it's starting to spin more and more, but let's say some of the material is spinning this way and some of the material is spinning this way. So there's an overall direction, but there's a lot of random motion mixed in there too. Well, if these different clouds are spinning different ways, when they run into each other, those clouds are going to end up kind of spinning in the same direction. If I have a cloud of dust and gas that's moving this way and a cloud of dust and gas that's moving this way, and those clouds run into each other, basically you're going to be left with those clouds ending up going in pretty much the same direction. So we're going to get this overall rotation of this cloud. So we're going to get the protostar in the middle and this disk of material around it. So we have our protostar. And what's called a protoplanetary disk. So again, this disk rotates faster and faster. Again, most of the material is still collapsing into the middle. That's where most of the mass goes. But some of that spinning material ends up forming this disk structure that we're not going to talk about the planet formation too much in this course, but that spinning material in that disk, some of that material might collapse together and form planets. So we have most of the mass in the middle, where the star is going to be. And in that disk, that's where we're going to start forming planets. They're all going to be spinning in the same direction in approximately the same plane. Kind of sounds like we're building a solar system here. So this is a computer simulation of one of these giant molecular clouds collapsing. So let me run this. So at the beginning, let me just kind of pause this for a second and get rid of those. What's being shown in this video is we've got the time up here. We've got different regions of this cloud, and it starts out, we start at the beginning, it starts out almost uniform. There's some regions that are slightly denser, some regions that are slightly less dense, and the coloring is representing how dense is that particular region of this giant molecular cloud. So as we start to play this and time starts going on, the cloud overall collapses a little bit, but those overdense regions are collapsing a lot faster. Instead of this being a nice smooth, everything collapses at once, those smaller regions are collapsing faster and starting to fracture off from each other. So the camera does a little swoopy thing here. We'll let that kind of play through. So I think it zooms in. Okay, so it's resetting the scale. So now the brighter regions are even more dense. You let it run a little bit more, and then I think it zooms in just a second. There we go. So now we're looking at some of the smaller cores that are being produced. And you can hopefully see a lot of this kind of spinning motion. This is the object was rotating, and as that mass was pulled in, it starts spinning faster and faster. And you'll notice that we're not forming a single star, we're forming a whole bunch of different stars. I also mentioned in one of the previous sessions that it's very common for us to see binary star systems where there are two stars, sometimes even sometimes 3 or 4 stars is not necessarily unheard of. And you can kind of tell why that's going to be the case, because these stars aren't forming in isolation. As these smaller clouds are collapsing, we're getting further fracturing and producing lots of smaller stars rather than just one gigantic star. So again, the things that we're looking at here are, instead of forming one giant star, we're forming lots of little stars. We're getting this rotation aspect that can form these disks around these protostars. And yeah, binary star systems are going to be very, very common. Again, this is over the course of, we're about 250,000 years into this simulation so far. But again, I think that shows the basics of some of these, some of the properties as this giant molecular cloud is collapsing, and some of these dense cores are actually starting to form protostars. And again, if you want to try this, have a look at this video yourself. It's available on YouTube by Matthew Bate. Okay, so let's talk about these protostars in a little bit more detail. So these protostars, how do we actually go from one of these dense cores into this new protostar? Well, as this core is collapsing, we said that originally, when it was still kind of a thin gas, thermal energy was easily radiated away. But as this thing becomes more dense, it's going to become more opaque. And as this protostar is collapsing, we're going to get a conversion of gravitational energy into thermal energy. So this protostar, it's literally powered by gravitational collapse. So powered by gravitational collapse. So basically gravitational energy into thermal energy. For each of these different kinds of stars that we're going to be talking about in these different stages of evolution, one of the things that I do want to focus on are what is actually powering this particular star. For main sequence stars, it's the fusion of hydrogen into helium in their cores. These protostars are not undergoing fusion yet. Okay? What's powering them, what's causing them to heat up, to continue to heat up, is this gravitational collapse that they're going through. So yeah, through conservation of energy, the gravitational potential energy is converted to thermal energy, and the protostar starts to heat up. So gravitational collapse is what is powering this protostar. And we've actually got some examples of images of these protostars. I believe these are also Hubble images. I'm going to eventually have to update these with images from the James Webb Space Telescope once those are, more fully available. But we can see these stars and these disks of gas around them. Some we're seeing pretty much face on, like this one over here. Let me zoom in on this so we can see this a bit better. So some of these we're seeing almost face on. Some of them we're seeing a little bit tilted. And some of them we're seeing almost edge on. This one we're seeing almost on its edge. This one's kind of a little bit tilted so you can see the protostar in the middle. But again, in all of these cases, it's the gravitational collapse of these objects that's actually powering the star and allowing it to continue to heat up. These protostars can be violent objects. We can sometimes see high-speed gas jets streaming off the rotational axes of these protostars. So again, this is an example of the protoplanetary disk is the part that's kind of a little bit blocked out. And then above and below that disk, like this would be, the protostar would be in the middle. And this gas is spinning around the protostar. And through a mechanism that's still not fully understood, this is one of the things that the James Webb Space Telescope is probably going to be studying as part of its mission. These spinning charged particles right next to the star can produce very, very strong magnetic fields in those two directions. And that seems to be what's powering these jets. So we can get strong jets and strong solar winds. So again, these protostars can be fairly violent. So, and as the protostar continues to collapse, these stellar winds are actually going to get stronger and stronger and eventually blow away that remaining cloud of gas. So this protoplanetary disk that was around the protostar and was starting to form planets, eventually this protostar, its stellar winds get strong enough to blow away any remaining material, leaving behind whatever planets have formed in that protoplanetary disk, and any things like asteroids, comets, things like that, little leftover remains of that planet formation process. So we've got this protostar. It's powered by gravitational collapse, so it's converting gravitational energy to thermal energy. But we want to know, how do we go from, we've talked about going from this giant molecular cloud to these protostars. How do we go from one of these protostars to a main sequence star? Well, let's talk about this for a bit. So main sequence. Again, we said there are two key properties for a star to be a main sequence star. So pause the video for a second and see if you can remember what those two properties are. So he said that main sequence stars are fusing hydrogen into helium in their core, using hydrogen to helium in core, and they are in gravitational equilibrium. The protostars, at first, are not at a high enough temperature and density to fuse hydrogen. And we're saying they're going through gravitational collapse. Gravity is still winning out and causing this thing to compress. So that is not gravitational equilibrium. Gravitational equilibrium is when these two forces, the inward gravitational force and that outward thermal pressure force, when those are balanced, we have gravitational equilibrium. But this protostar, it's still continuing to collapse and continuing to heat up. In order for fusion to happen, we said hydrogen nuclei, protons, they're positively charged. They don't like being close to each other. They will electrically repel each other. But if I can get those protons to be densely packed enough, so they're all really close to each other, and I can increase the temperature so they're moving around really fast, then eventually they're going to be going fast enough and are close enough together to start to go through fusion. Well, in this protostar, we've got a lot of material that's continuing to collapse under gravity, continuing to heat up, and in the core of that object, we're eventually going to get the conditions to actually go through this fusion reaction. So eventually, the conditions in this protostar are eventually going to allow hydrogen fusion to occur. So core heating and compressing, we eventually get conditions to fuse hydrogen. So let's say this protostar core is collapsing, it's heating up, it's getting more dense, and eventually it can fuse hydrogen. So the first time that 4 hydrogen nuclei come together to form 1 helium nuclei, does that mean that we have a main sequence star yet? Well, probably not yet. Because at that point, we would have hydrogen being fused into helium in the core, but that first reaction is probably not going to achieve balance in the star yet. So that core is going to continue to collapse, that fusion rate is going to continue to increase, and eventually, the energy that's produced by the core is going to provide enough thermal pressure to balance out that gravitational collapse. And finally, we have gravitational equilibrium established. So when we go from this protostar to a main sequence star, that is when the core fusion rate matches the energy released at the surface. Basically, the core fusion and gravitational equilibrium, both of those conditions are met. That's when we go from a protostar to a main sequence star. So, how long do these protostars last? Well, the masses of these protostars range from about 8% the mass of our sun to around 1,000 solar masses. not 1,000 solar masses, around 100 solar masses. And depending on the mass of the protostar, it can vary quite dramatically in how long it takes these protostars to form. Low mass protostars can take millions of years to form. High mass protostars can take only, a few tens of thousands of years to form. And these formation lifetimes are always less than about 0.1% of the main sequence lifetime. So for example, it probably took our sun around 50 million years to go through its protostar phase, but we expect it to be a main sequence star for around 10 billion years. So the formation time is always significantly less than the main sequence lifetime. And to such a high degree that some of these high mass stars, remember, the high mass stars also have short main sequence lifetimes. Some of these high mass stars might have formed, gone through their main sequence lifetimes, gone through their supergiant phases, and died off before these low mass main sequence stars have even fully formed. That's kind of how different these formation times are. So let me write a little bit of this information down. So for protostars, high mass form quickly. Actually, let me set it up like this. Let's do a comparison between high mass and low mass. Let's do this side by side. So high mass stars form quickly. Low mass stars form slowly. Basically the same kind of pattern that we talked about for the main sequence lifetimes. High mass main sequence stars are going to last only a relatively short time. Low mass main sequence stars are going to stick around for a lot longer. High mass stars, well, only a few of them form. So low numbers. And low mass stars form in significantly higher numbers. So this graph is trying to represent approximately how many stars will form for different solar masses. If I have a low solar mass, lots of stars are going to form. These are different models trying to make these estimations. Low mass stars will form in much greater numbers. High mass stars are going to form in much smaller numbers. So we get many more low mass stars being produced than high mass stars. These low mass stars live a very long life, live much longer. So these low mass main sequence stars are very, very common. When we look at the HR diagram, I mentioned that those low mass main sequence stars are very, very common because they're produced in larger numbers and they just last a much longer time. There's actually a limit on how high mass these stars can be. Remember how I said that for protostars, they can have these strong jets and solar winds that eventually push away material. Well, if I try to form a star that's more than 100 or 150 solar masses, if it's much larger than that, then the protostar that's trying to collapse to form a very, very high mass star, like something over 200 solar masses, as it's trying to form, the solar winds that it's producing are so strong that it will actually blow away any further layers from trying to collapse onto this star and add to its mass. So approximately around 100 or 150 solar masses, that's pretty much the upper limit of the masses of stars that we see in our galaxy. For protostars with too little mass, less than about 0.08 times the mass of our sun, well, we said that these protostars, as they collapse, they're converting gravitational energy to thermal energy in their core. So their cores are heating up and their cores are getting more and more dense. Well, if these protostars don't have enough mass, then their cores are never going to get dense enough and hot enough to actually go through hydrogen fusion. So for these protostars with too little mass, they're going to form into brown dwarfs. So let's talk about brown dwarfs. So a brown dwarf. So too little mass. So less than 0.08 times the mass of the sun to actually get core fusion to occur. They don't have enough gravitational energy to generate those high temperatures. They don't reach a high enough density to actually, again, achieve fusion reactions. So these failed stars are known as brown dwarfs. And the thing that supports them against collapse is something that I mentioned in the topic on the HR diagram when we talked briefly about white dwarfs. These brown dwarfs are supported by this electron degeneracy pressure. So the cores are supported by electron degeneracy pressure. Which is basically the electrons in this object don't want to be in the same quantum state. So electrons don't want to be in the same state. And this effect produces an outward pressure. Which is kind of a wild idea in that the same mechanism through which electrons in an individual atom will not want to be in the same quantum state. This is a situation where we have a whole bunch of material compressed down so small that the electrons in that entire thing are all kind of interacting with each other in this way where they don't want to be in the same quantum state. So they produce this outward pressure to support them against further collapse. These brown dwarfs are only slightly larger than Jupiter, and they have relatively low surface temperatures that will eventually cool down even more over time. Now, these brown dwarfs never get very luminous. Again, they never achieve a fusion reaction. The core is collapsing and heating up, and eventually it just, okay, we can't really collapse anymore. The core is supported by this electron degeneracy pressure. There's no more energy production, so it's just radiating away that last little bit of energy and never gets very luminous, never gets very hot either. And most of this energy, if these are relatively low temperature objects, most of their energy is again most of their light is going to be given off in the infrared part of the spectrum. So if we have this image, if we change this to looking at an infrared image of the object, we see there are way more brown dwarfs there than we might have originally expected. So these objects are very hard to detect with visible light, but more modern telescopes that have started looking at the sky in the infrared part of the spectrum, especially these more space-based observatories, again, the James Webb Space Telescope should be excellent at being able to do this because it looks partly into the infrared. This has allowed us to detect how many brown dwarfs are out there, and it's possible that brown dwarfs outnumber all other stars Again, we said that these low mass objects are formed in much higher numbers. So these brown dwarfs might be very, very common. The first brown dwarf that was directly detected, this is some images from the Palomar Observatory and the Hubble Space Telescope, were some of the first ones that were directly imaged. This first brown dwarf was discovered about 18 light years away, that orbits around another star. So this is a Gliese 229, and this is the brown dwarf that's in orbit around that star. This was a binary star system, but one of the stars in that pair didn't have enough mass to actually become a main sequence star. Again, we can use infrared light. This is actually observing the orbit of one of these brown dwarfs around another object. This is from NASA's Spitzer Space Telescope. And again, these brown dwarfs have masses only 20 and 50 times the mass of Jupiter in some of these images. We've got two examples of brown dwarfs imaged by the Spitzer Space Telescope. So to kind of finish this off, let's talk about this in terms of the HR diagram as the star is trying to form. So this protostar, originally it's going to be at a low temperature, so far off to the right on this diagram, and not very luminous. But as the protostar is continuing to collapse under gravity, the temperature is going to go up, so it's going to move further and further to the left on this diagram. The temperature is going to increase, and it's going to start becoming more luminous. As it continues to heat up, eventually it reaches the temperature where there's now a fusion reaction that's going on inside of the core, which starts to rein in that gravitational collapse because there's a new source of energy. And as that protostar continues to collapse and get more and more thermal energy, eventually the fusion rate's going to increase in the core, and eventually this is going to become a main sequence star. Okay. And when we look at these very, very young star systems, we were looking at a session or two ago, we were looking at star clusters. And in those very, very young star clusters, we can actually see stars that are still in the protostar phase, and we can track how those objects move. When comparing different star clusters, we can track how those objects tend to move on this HR diagram. And lastly, let's say there were some stars in here that did not have enough mass and were destined to become brown dwarfs. Think about where on the HR diagram we might find brown dwarfs. So pause the video and think, where on the HR diagram would we find brown dwarfs? Or if it was off the HR diagram somewhere, where off of the diagram would it be? Well, if we're dealing with these brown dwarfs, we said they have a very low surface temperature and they never get very luminous. So if it has a very, very low surface temperature and never gets very luminous, well, it's going to have to be even further to the right on this diagram because, again, spectral class O is the hottest temperature. Spectral class M is the lowest temperature. So these brown dwarfs, if they're very dim, they have to be off scale on the bottom of the graph. And if they're at low temperatures, they're also going to be off to the right side of that graph at very, very low temperatures. So kind of continuing this pattern of we've got these low mass main sequence stars, and eventually it's not a main sequence star anymore, it's a brown dwarf down here. So that's kind of the different properties of star formation. And in subsequent sessions, we're going to be talking about, once we have a main sequence star, what happens to low mass main sequence stars, what happens to high mass main sequence stars, and what happens to all these types of stars when they eventually reach the end of their lives. So we'll do that in future sessions.